The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Thank you. So, okay, let's continue with vectors and operations on them. So remember, yesterday, we saw the topic yesterday was dot product. And remember the definition of dot product. Well, the dot product of two vectors is obtained by multiplying the first component with the first component, the second with the second, and so on, and summing these, and you get a scalar. And the geometric interpretation of that is that you can also take the length of A, take the length of B, multiply them, and multiply that by the cosine of the angle between the two vectors. So we've seen several applications of that. So one application is to find lengths and angles. So, for example, well, you can use this relation to give you that the cosine of the angle between two vectors is their dot product divided by the product of the lengths. Another application that we have is to detect whether two vectors are perpendicular. So to decide if two vectors are perpendicular to each other, all we have to do is compute their dot product and see if we get 0. Okay. And well, one third application that we didn't have time to discuss yesterday, that I will mention very quickly, is to find components of, so let's say find the component of a vector A along a direction U, so some unit vector. So let me explain. Let's say that I have some direction, for example, the horizontal axis on this blackboard, but it could be any direction in space. And to describe this direction, maybe I have a unit vector along this axis. Let's say that I have any other vector A, and I want to find out what is the component of A along U. So that means what is the length of this projection of A to the given direction. Okay, so this thing here is the component of A along U. Well, how do we find that? Well, we know that here we have a right angle, so this component is just length A times cosine of the angle between A and U. But now that means actually we can compute it very easily because, well, I could, that's the same as length A times length U times cosine theta, because U is a unit vector. It's a unit vector. That means this is equal to 1. And so that's the same as the dot product between A and U. Okay? So that's very easy. I mean, of course, the most obvious cases of that is, say, for example, we want just to find the component along I hat, the first axis, the unit vector along the x-axis. Then you do the dot product with I hat, which is 1, 0, 0. What you get is the first component. and that's indeed the x component of a vector. Similarly, say you want the z component, you do the dot product with k, that gives you the last component of your vector. But the same works with a unit vector in any direction. Okay, so what's an application of that? Well, for example, in physics, maybe you have seen situations where you have a pendulum that swings, so you have maybe some mass at the end of a string, and that mass swings back and forth on a circle. And to analyze this mechanically, you want to use, of course, Newton's laws of mechanics, and you want to use, well, forces and so on. But I claim that components of vectors are useful here to understand what happens geometrically. So what are the forces exerted on this pendulum? Well, there's its weight, which usually points downwards. And there's the tension of the string, and these two forces together are what explains how this pendulum is going to move back and forth. Now, you could try to understand the equations of motion using xy coordinates, or maybe xz, or whatever you want to call them, let's say xy. But really, what causes the pendulum to swing back and forth, and also to somehow stay at constant distance, are phenomena relative to this circular trajectory. So, for example, maybe instead of taking components along the x and y axes, we want to look at two other unit vectors. So we can look at a vector, let's call it t, that's tangent to the trajectory. Sorry, can you read that? Maybe it's not very readable. So t is tangent to the trajectory. And on the other hand, we can introduce another vector. Let's call that n. And that one is normal or perpendicular to the trajectory. And so now, if you think about it, you can look at the components of the weight along the tangent direction and along the normal direction. And so the component of F along the tangent direction is what causes acceleration in the direction along the trajectory. It's what causes the pendulum to swing back and forth. And the component along n, on the other hand, so that's the part of the weight that tends to pull our mass away from this point, is what's going to be responsible for the tension of the string. It's why the string is taut and not actually slack and with things moving all over the place. So that one is responsible for the tension of a string. And now, of course, if you want to compute things, well, maybe you will call this angle theta, and then you will express things explicitly using sines and cosines, and you will solve for the equations of motion. Okay, that would be a very interesting physics problem, but to save time, we're not going to do it. I'm sure you've seen that in 801 or similar classes. And so to find these components, we would just do dot products.